Thank you. Welcome to the webinar today, Edge Computing and AI, Software-Defined Sensors. My name is Karen Larson and I work for DPI, Discovery Partners Institute, which is a division of the University of Illinois system. DPI is one of two partner organizations working on TechReady Illinois, which is hosting the webinar today. And before we begin, before we get into the main portion of the webinar, let me tell you a little bit about TechReady. So DPI had originally planned to launch a workforce development initiative later in 2021. Then, as we all know, COVID-19 came along and blew everything up. With so many people unemployed in the state and across the country, we knew that we needed to pull that launch forward right away. We partnered with another local group, P33, and brought TechReady to light very quickly. TechReady is focused on increasing the availability and access to training programs in high demand tech fields. We also, across all of our programs, most of them include certificates, and many of them also include a student experience, including study groups, coaching, and project opportunities for hands-on learning. We've curated all of our programming with leading employer-driven input. We've grouped our programs into 4 learning tracks that include data analytics, cloud computing, software development, and cybersecurity. In total, we have 10 providers delivering over 20 programs that include content for all skill levels from introductory to advanced. They run from a full weekend to 32 weeks of learning and from free to several $1,000s for a full certificate. To learn more, visit us at techreadyillinois.com. So now let's get into the subject at hand. The continual exponential improvement in processing power of ever smaller form factors enables a new approach to measuring our world. Today, it is possible to co-locate sensors and powerful computers at the edge of the network, enabling us to program the sensors to analyze data in place, greatly reducing the amount of data that must be transmitted. For example, today's programmable or software-defined sensors enable us to extract measurements from images. For example, statistics about pedestrian flow or vehicle flows, or sound, for example, frequency of loud noise events. With next generation computing hardware, these intelligent sensors will be programmed to learn about their surroundings in order to detect unusual events and conditions. For instance, to collect more detailed data during those events. Chicago, through DPI scientists and collaborators at partner institutions like Argonne, Northwestern, and the University of Chicago, is at the forefront of this research, embedding software-defined sensors in urban, rural, and environmental settings to support research ranging from urban to ecological to extreme weather research. Our speaker today is Charlie Catlett. Charlie joined DPI as a senior research scientist after 2 decades as a senior computer scientist at the U.S. Department of Energy's Argonne National Laboratory. He's also a senior fellow at the University of Chicago's Mansueto Institute for Urban Innovation. His current research focuses on urban data analytics, urban modeling, and the design and use of sensing and AI at the edge computing technologies embedded in urban infrastructure and the environment. Among some of his awards, Charlie was recognized as one of Chicago's Tech 50 technology leaders and as one of 25 doers, dreamers, and drivers of 2016. He is also a computer engineering graduate of the University of Illinois at Urbana-Champaign. Please join me in welcoming Charlie Catlett. So now I will stop sharing my screen and let Charlie start to share his screen.
Thank you, Karen.
Thank you for joining us.
Okay, off we go. So I want to talk about a couple of projects in this area of what we have started to call software-defined sensors. That's a little bit of a play on words. There is a technology you may be familiar with called software-defined radios, which means that it's a radio that, based on the programming that you put into it, can listen to different frequencies and different framing and formatting of those frequencies. So with the change of software, you could turn a software-defined radio from an AM radio to listen to a sporting game to a cellular radio to make a phone call, or with a different set of programming, turn it into a Wi-Fi hotspot. And those kind of capabilities are typically hardwired into the modem or transmitters of radios. And so software defined means it's not hardware defined, but software and programmed. And we think of this in the same way with sensors. A typical sensor network would be you buy some sensors, they do one thing, they take a temperature or they take a concentration of a gas, you put them out into a sensor network, and then that's what you measure. But you don't have a way, without edge computing, you don't have a way to change what you're measuring. And then the other thing about software-defined sensors is that it lets us measure things that we wouldn't be able to measure with traditional sensors. So I'll talk about a project called the Array of Things. The notion of using Internet of Things in an array of similar instruments, just like an array telescope, is where that name came from. Array of Things is a project that is just transitioning to sort of steady state. The funding was from the National Science Foundation. It was a project that I initiated about 7 or 8 years ago while I was at UChicago and Argonne. And it involves partners that you see on the screen here: Northern Illinois, Northwestern, UChicago, Argonne, University of Illinois at Urbana-Champaign. And then there's a new project that I'll also talk about that is a sort of follow-on to the Array of Things, and that's called SAGE. And that is the same team that you see here on the map, but it's expanded as we've included partners from both coasts and throughout the US. So I'll talk a little bit about that, but mostly I want to talk about why we considered this software-defined sensor concept, what we were motivated to do, what we've done in Chicago, and then where we're going. Now, most of the time in the last 10 years or so, when we've talked about measuring cities, it's been either explicitly or assumed to be part of a smart city initiative or goal of making cities smarter. I have not used that term much in the last decade or so, because it oftentimes has the connotation that by adding technologies to cities, we can solve some of the most vexing problems that urban areas have. And some of the most vexing challenges that we have in urban areas are not technological challenges. So on the other hand, while we can't perhaps solve those problems with technology, we can provide better data to go toward the understanding of those challenges and possibly toward solutions. So our idea was to create a measurement system that didn't exist for cities, and to look at how that could be designed and how that could operate in steady state. So, you've already, as I've been talking, you've probably skimmed the screen here. We were able to, Mayor Emanuel is a big fan of our project, and when Mayor Khan from London came, we had the opportunity to talk about the project. And both of those mayors, I think, characterized the approach to technology in cities, and that their emphasis is on the use of technology and data to make lives better for people who live in cities. Now, every mayor has aspirations, and it's a hard job, but we relied on the support of the mayor's office and of the current mayor of Chicago, Mayor Lightfoot, for this project. And I think we've gotten their support because we've emphasized measurement, we've emphasized open data, we have taken privacy very seriously, and we've tried to do the project in a way that engages residents and engages youth through schools. And I'll talk a little bit about each of those things as we go forward. So why do we want to measure a whole city, and why would we need 50 or 100 or several hundred devices to do that? When you look at the characterization of a city along different facets, whether it's life expectancy or health, or maybe it's access to services or healthy food, what you see are maps like these where cities are heterogeneous entities that are made up of neighborhoods within which you experience different levels of crime or air pollutants, or different access to public transit, different access to other opportunities. So where you live in a city really has a huge impact on your experience as a resident of a city. And in order to understand a heterogeneous entity like a city, we couldn't just put up a couple of devices to measure things like air quality or traffic flow. We needed to have a strategy that would give people studying cities or making policy, that would give them enough spatial and temporal resolution to get a better picture of the city than we might have today. So you see these maps on here, and maybe they're fairly self-explanatory. On the left, incidence of asthma by neighborhood. In the access to services, that is a color-coded map of the city according to the amount of time it takes by public transit to get from any point in the city into the Chicago Loop. And you can see if you're in one of those green areas, you're well served by public transit, not so much if you're in a purple area or in those yellow areas. And the one on the right, access to healthy food, it's a composite map. The areas that are shaded are ones where there are no supermarkets that are larger than 2,000 square feet. And that choice of 2,000 square feet is a proxy for, is there fresh produce and healthy food in the neighborhood? Because a smaller store, a convenience store, for example, wouldn't have a fresh produce section or other sorts of healthy foods. You might be able to get a microwave burrito. If I showed you a map of the density of fast food, translation high sodium, high cholesterol, high fat foods, the map would be white because they're just everywhere. And then the crosshatch show African American communities. And so what you see with this map is that predominantly, if you're in an African American community, you're not having access to healthy food in the same way that other communities are. And so this feeds into health issues like hypertension or cardiovascular or pulmonary issues that contribute to this heterogeneous nature of cities. So here you see 4 different ways to look at cities, and you could imagine, as there are, at least 4 different science communities that are interested in measurements related to these things. And along with that, typically the science community is interested in the same things that residents are interested in, and ideally that local government is interested in. So with that notion of cities being these collections of neighborhoods, we began almost 8 years ago, really, to have conversations with different science communities. And by that, I mean a whole bunch of social scientists or a whole group of transportation scientists or climate faculty members. So those different science communities, we started having workshops, and then we also had workshops with community groups and with different departments within the city of Chicago. And we asked a similar question to these. In some cases, what do you want to measure? In other cases, like when we were talking to computer scientists, we asked what would, if we could put 100 or 200 devices throughout a city, what would those devices do that would help you in your research and development in developing new technologies or services? And similarly with the other groups, what would you want to measure? What is the most important set of things that we should measure in a city in order for you to answer your question about how does green space affect crime or urban hotspots in a heat wave? Which parts of the city are most impacted in terms of the health of residents, or where are the intersections in the city that are the highest rates of traffic crashes? So from these discussions, we got this long list of things to measure with sensors on the left, but then we had this list on the right where there's not really a pedestrian flow sensor that I can go to, the electronics store and buy a, pedestrian flow sensor or a pattern of public use sensor, how people use parks. So those are really things that you would typically measure through a human observation. And in fact, if you want to know about traffic flow in Chicago or other cities, largely that's going to come from somebody standing on the corner for an entire day taking notes of where traffic is coming and going. They do have those hoses that they run across the street, but a lot of these observations are still today human observations. So we said, hey, we could do more than just a sensor network. Why don't we think about putting a processor out there with the sensor and being able to do image processing or sound processing? Now, one of the reasons we also wanted to get this high resolution, both spatial and temporal, is that increasingly what we're seeing as the research community looking at health and air quality as an example is finding that even on a day-to-day or hour-by-hour basis, air quality or air pollution can have an impact on human performance, whether it's students in school or people trying to make a decision about interactions or what they want to do at a given point in the day. And the fact that you can see these natural experiments that have been done where even moving school children from downwind to upwind of a pollution source has a more or less immediate impact on their ability to learn and behave in school. So that's why we decided, okay, for many of these measurements, whether it's noise or air quality, we really need a lot of devices in the city, and we need them to give us measurements, not just once a day, but once a minute or even more often than that. So these all went into the design of a device that you see on the left-hand side there. There are now about 130 of them up throughout the city of Chicago. They're about 8 meters above the ground, about 24 to 28 feet. They're pretty small when you look at them there, when you have one on the table. I don't have one here, but they're pretty large. They're 14 by 14 by 9 inches. So they're not very conspicuous. We looked around in 2013, 2014, and we couldn't find anything that would do what we were needing to do. So we were faced with the decision to either not do the project or come up with something and design our own device. So we partnered with not just the institutions I've mentioned, but we got funding from U Chicago and Argonne, and we had a partnership with the School of the Art Institute of Chicago to do the physical design. And so we came up with this device. We finally started to get them out onto the street about this time 4 years ago in August of 2016. And we translated those measurements that people asked for into specific sensors that you see here. And then we included microprocessors, so actually fully programmable Linux devices inside these units that we could program from a central location from afar. So that allowed us to begin to look at how do we do a software-defined sensor for flooding or for traffic flow, or even for something like what percentage of bicyclists are wearing helmets. Do we, if you're the Department of Public Transit, Department of Transportation or Park District, maybe you want to run a campaign to encourage people to use helmets, but you want to run it in a part of the city where most of the bicyclists are not wearing helmets. So the device then, does both sensing and computing. The sensors are useful. There's nothing wrong with a sensor network. There's a lot of things that you can learn from just simple sensors. And this is an example. We partnered with University of Chicago's National Opinion Research Center, or NORC. This is a group of about 2,600 employees and 300 data scientists. And they worked with us, so we were already working with them on some air quality as input to some social science research, as you can see by some of the publications there. But the question here was, when the state of Illinois did the stay-at-home order and traffic in and out of the city of Chicago didn't dry up, but it went down quite a bit, did that have an impact on air quality? Interestingly, it did, but we had to tease that impact out from the normal seasonal changes, because in fact, normally around April or May, a lot of air quality gets better. A lot of the pollutants are less prevalent in the spring. And so we were already going to see better air quality in the spring, but the stay-at-home did have an impact. And across the country and around the world, people have been trying to figure out what the benefits to air quality have been, and they've been significant to the stay-at-home and now the virtual work period of time that we're in. So how do we do the software-defined sensors? So I think of just most of what we're doing is looking at the cameras. So these devices that are up on the poles have in the blue box a couple of processing units. One of them is just a Linux device that takes care of all the data management and system management. It samples the sensor boards and reports that data to the mothership, to a big database that we run at Argonne National Lab. And then there's a camera along with some light sensors. You may have noticed on the list, we have ambient light, visible light, ultraviolet and infrared. Those sensors are pointed straight up from the top of the blue box along with a camera where, as I'll show you in a moment, we've been doing some research in figuring out what's happening above our heads. And then the most interesting one, I think, for most scientists is the one that's pointed down. FOV here is field of view, so it's a 75-degree field of view looking up, but 170-degree field of view looking down. So on the left-hand side here, you can see a couple of rows of images from two different devices. The top one just, you can see just what the cameras are seeing, and the bottom one, a little bit of processing to do object recognition and color code things that we see, or I should say the software that's running on the device sees in those images. Typically, we've been typically pulling one image every 15 minutes and storing it in a training database. And by that, I mean to train the algorithms that we're using for AI or machine learning. And maybe oversimplification, a machine learning algorithm is a neural network that has many layers of processing. That input goes through and then out at the other side says, yes, there's a car, or yes, there's a cat. And to train that neural network, you have to show it lots and lots of images. In this case, if we want to recognize a bus, we have to show thousands, ideally hundreds of thousands of images to that neural network so that it can learn which ones have from training, where it says, okay, this one has a bus and this one doesn't, and I know this. And then I train on known data like that, supervised learning. And then our neural network can now recognize a bus. So every 15 minutes we pull an image, we put it into a very highly secure database. You can only get access to it with a signed data use agreement. We've been taking images a little more often, I believe in some cases every 3 to 4 minutes in the city lately, because of some of the work that we're wanting to do with those images I'll mention in a moment. But anyway, so here you can see what the strategy is for the cameras in the devices. There's a very strong privacy policy that I'll talk about in a moment. On the right-hand side here is a new device that's not one of the array of things devices, it's the next generation, and that is the front gate of Argonne National Laboratory. We've had a next generation of our device up there since about December last year, and are using it for some of the training images and even for developing some algorithms. You see here a simple one that says, hey, draw a box around a vehicle and follow it through the screen. On the left-hand side, you see many examples from the broader science community of the kinds of things that scientists want to do with images. Recognizing flooding, sure, you could put moisture sensors throughout the city. It'd be an unwieldy proposition and quite expensive, or you can point a camera and train an AI neural network to recognize standing water. More recently, in the lower right, we've been interested in whether these devices that we have throughout the city, these are images from the array of things at the lower right, as is the traffic flow. And, you know, can we tell whether people are social distancing? Well, sort of. I mean, we can tell that the 6 people in the lower left, or in the middle left there, middle of the screen, we can tell that they're not social distancing, but we don't know anything about these people. And so for all we know, it's all people in the same family who don't need to be social distancing. So that's a little bit difficult to do with just cameras. On the other hand, oftentimes we can tell if somebody is wearing a face mask or not. So in principle, we could develop a face mask counting capability that would tell the city of Chicago what percentage of pedestrians throughout the city are wearing a mask outside. And that, oftentimes people aren't wearing them outside, so they may still be wearing them inside. So, limited amount of information there. You notice it says faces and these images are blurred for privacy. In order to put software into an array of things device, a scientist or a group that we would be working with, maybe it could be a company or even the city of Chicago, has to say, here is what we're going to do with the images and here's why. We are going to check to see what percentage of people are wearing face masks so that we can get a good feel for compliance with personal protective equipment. If somebody were to propose, we are going to find out who's not wearing face masks, that would be rejected. So the privacy policies reject anything that would try to identify an individual. And then the way that we would guard against that is we actually, it's scaled at this point, that we could actually examine the code before it gets put out there. There's more protections that are built into the device. When you put your software out at the edge, and let's say your software is this one in the lower right, you're gonna try to recognize people who have face masks. So what that means is you just need to report two numbers, the number of people in the scene and the number who have face masks. If you try to report something different than those, the software that governs the device, the array of things node, will simply not report that. So you can report two integers, but that's all you can report. And in fact, if you try to report something else or your software tries to report something else, a red flag will go up to our staff. So, from the architecture on up, we've really thought carefully about, we're going to put cameras out in the public way. We want to make sure that it is a system that protects people's privacy. I mentioned the upward facing. This is a project here that some of the folks at Argonne did with some visitors from the Air Force. The question here was, can we tell the difference, just as a proof of concept? Can we tell the difference between a drone, a bird, and an airplane? And the answer is yes, but not because of their shapes, as we did in the previous screen looking at cars or vehicles, but because of the characteristics of movement. And so this is why, this is why it became important to be able to spot an object in the image, and then in the next image, whether it's a video like this, which is like 10 frames a second, or if it's just one frame every minute or every 20 minutes, to be able to say that's the same object in the next frame, because we might want to look at the movement characteristics as we did here with trying to detect drones. And this was in partnership with Soldier Field as well, because if you're having an event in Soldier Field, you would kind of like to know that there's a drone incoming, coming in from the parking lot. This is some work at Northern Illinois University here. I mentioned Pedestrian Flow. Here, what they're doing is counting the number of people that come through, the number of people who cross the road, and how many of those use the crosswalk. And then with historic data, they can do other sorts of analysis, like this one here, where blue is a pedestrian, a blue line is a pedestrian coming in one direction, and red is in another direction. And so, this is moderately interesting, I suppose, but if you're interested in traffic safety, you might say, well, this is a crossing that, maybe we should rethink the crosswalk, because there's so many students that are going sort of catty corner. And so maybe this is the place where we need to put, if it was a signal intersection, a scramble crosswalk like you see at Jackson and State, where all of the walk comes on at the same time, all traffic stops, and people can walk across in any direction. So an example of the use of an array of things device. I don't have images here, but you can see there's water down there. And another group of students and faculty members at NIU also use the same images and the same device to track the water depth of that water underneath the bridge. I said we have about 130 devices in Chicago. We have also devices in DeKalb, as you can see here. We have them in Nashville at Vanderbilt University. We have Georgia Tech has some down in, they've actually put theirs in Columbus, Georgia. We also have partners overseas in Bristol, England. There are array of things devices, and you can see some images in the lower left from Taichung City in Taiwan. So there's a growing community of scientists around the world who are interested in using these software-defined sensors to make sense of what's happening in cities and even outside of cities. Now, one thing that you don't get from traffic reports is something called a near miss. You get, if somebody gets hit by a train, you get a notice about that. But how many times do people almost get hit by trains, right? So here's a person walking across, nothing, to report home about. She doesn't get hit by the train, but that's a near miss. And so wouldn't it be good if our intersections were smart enough to keep track of near misses and not just particular events? And as a teaser, I'm not going to leave that up. Well, maybe I will. I'll let you see it one more time. I don't know why she doesn't see it coming from the left there, but it's good that she was able to be quick on her feet and get out of the way of that train. That's from Auckland, New Zealand. Now, there are lots of projects that are using the array of things technology that have started up in the last few years, separate from the Array of Things project, which was funded by the National Science Foundation with corporate partners and cost sharing from the city of Chicago, as I'll mention in a moment here. But there are other projects too that are using this technology that we developed. One you can see here on the left, the Illinois Department of Transportation. You just saw a pedestrian crossing. There are, I don't know how many hundred at-grade crossings throughout Chicago, and each of them represents a opportunity for rail crossing, for rail traffic to impact the flow of vehicle traffic. And so if you want to reduce the number of at-grade crossings, a very expensive thing to do by making an overpass or an underpass, which ones do you prioritize? If you have a fixed amount of dollars, let's say $1 billion, you can't fix them all. So Illinois Department of Transportation came to us and said, how about, can you tell us, not just, we can already know when the gate goes up and when the gate comes down, but can you tell us after the gate goes down and comes back up again, how many vehicles were affected by that crossing? How many of those vehicles were emergency vehicles or public transit? And how long does it take after the crossing completes and the gate goes back up? How long does it take before traffic returns to steady state? So these are observations that need to be done. And so a software-defined sensor that looks at the row of vehicles every time the gate goes down and understands what steady state is. What is steady state when there's no crossing happening? So an intelligent device that can do that is quite useful. Flooding, I've talked about a little bit. We've got some projects with US industry and predictive maintenance in the power grid with software-defined sensors distributed throughout the infrastructure. And then classifying and quantifying road, rail, and public transit traffic in and out of O'Hare. The rideshare companies have sort of come out of they've come clean with the fact that they are explicitly competing with public transit. And that has had an impact on traffic in and out of O'Hare. So the city of Chicago and the state of Illinois and Department of Energy have funded a project at Argonne to put up 50 or so devices like these. They'll be the new kind, so that we can measure in great detail traffic coming in and out of the airport, and then develop a computer model, a simulation model that allows the city or the airport to do what if scenarios with different policies that might give incentives to people to take the blue line train instead of a ride share or driving a private vehicle. So those are examples where software-defined sensors are very useful. It's more than what you can get from just a hose across the highway that counts the number of wheels that hit it. Moving down the road, the Array of Things devices have, because we've had to manufacture them in quantity, we had to lock into a processor that's now a couple of years old. And still we're seeing in consumer electronics and the kind of processors that we're using, we're seeing a doubling in price performance, the same price, double the performance, or for every 18 to 24 months. And so even after 2 years, we start to look at these processors and go, well, it's fine for counting the pedestrians at NIU, but what if we want to do something more sophisticated, like characterize the way that interactions are happening in a public space? Even something like uh, uh, looking at whether two people in the park are having a normal interaction or whether they're having a tense interaction. This is difficult to do without very, very powerful AI and machine learning code, but people are developing these. And one of the advantages to the edge devices is that as people develop these capabilities with more powerful machines like cloud systems or ones that are in the data center, once the processing power becomes fast enough at the edge, we can start to move those capabilities out. So there's a queue of new capabilities that are really just waiting until the edge computers get fast enough. Now, the devices that we've been putting up in testing at, like the one at the Argonne gate, the processing power in those devices is something like 200 to 300 times faster, more powerful, larger memory than the ones that are in the Array of Things devices that are up now. And I say 200 to 300 times faster because depending on the algorithm that we're using, we're seeing anywhere from a 60 times speed up to a 300 times speed up. So that's encouraging. It's also the case that most of the computer vision codes that are being developed are using what I would call ideally convenient camera angles. So you see these right here, the laboratory experiments are doing a line of sight that is at 5 or 6 feet off the ground. And people look different when you're looking down from 28 feet off the ground, as do vehicles. So when we look at the confidence level of our AI code that says, is this a Tesla or a Ford or a BMW, that confidence level might be in the 80 to 90% that we got the answer right when we're going through standard images of cars, which are normally taken from the vehicle manufacturing website. So they're perfect angles at the front or side of the car. But when you go up even 28 feet and come at that angle, the confidence level of those same algorithms goes down into 40 or 50% confidence. So we've got to somehow make up for that difference in angle. I mean, a simple example is a person. You can see what a person looks like. It's, a person is a thing that's like 5 feet tall. But when you're looking down from above, people are, very short. And on rainy days, they turn into octagons, right? So there's a challenge still with doing software-defined sensing out in the field in how we train these neural networks. Now, just continuing to talk about social and behavioral experiments that could be done, you see here 6 different cities, all of which have Array of Things devices in them. Actually, it's not Atlanta, it's Columbus, as I mentioned. The plan was originally Atlanta. And so we've been working with other groups, universities in other cities, in some cases national laboratories, to say, hey, what if we were to set up experimental venues in dozens of cities around the world, different population density and size, different climate, different culture, different topology. But we set up in similar venues like you see here, a couple of different options like in DeKalb and Taichung City, those are marketplaces, or in Atlanta, a marketplace, or maybe a park where people gather like Crown Fountain in Chicago or some equivalent in Nashville. So if you had those consistent venues where you were instrumented with these devices, then a social scientist could do repeatable experiments. They could say, well, how far do people normally stand apart from each other as they're walking or talking in a marketplace? And does that differ by population? That might have been just a curiosity, who cares how far people are when they talk to each other 6 months ago, but today it's a pretty important thing, right? If you've got a culture that normally speaks, 2 feet away, then you've got to work against that culture to keep people, 3 to 6 feet away. So this is one of the future objectives of the new project that follows the Array of Things that started last fall. So let me just close with a couple things. One is some logistics of what we've done in Chicago. CDOT, the Department of Transportation, has been our primary partner, but we've had partners not just with the Department of Transportation, but with other departments and even with companies. And furthermore, this is not just, I mean, when people talk to me about smart city projects or equivalent projects in other cities, I say, you know, this is not about an MOU with the city, a memo of understanding or something that gets ceremonially signed by a university president and a mayor. It's really about relationships, and what we've been able to do in the last 7 or 8 years is establish collaborative relationships with everyone in the city of Chicago, in this case, the Department of Transportation, from the commissioner, and we're on the 3rd commissioner that we've worked, actually the 4th commissioner that we've worked with, all the way through the 9 layers of management to the guys like Jimmy here that go up in the lift and actually install the devices. And what each of those layers of management, if you will, have seen is that there's a benefit to them, to these kind of projects. And so they've been enthusiastic partners. There you see 130 devices, those dots there. Some are clustered around specific experiments in the south part of the city there, and that is the Chatham neighborhood, the sort of right angle with a few to the north. That's the Chatham neighborhood where there's a lot of flooding. You can see a cluster around Little Village on the southwest side, on either side of the canal and Interstate 55, the Stevenson. That is looking at air quality. And then of course downtown in the Loop, you can imagine that that's where we get the most pedestrian traffic. You can also see just to the northwest of the Loop a ring around, oblong ring around Goose Island. That was also intentional to look at traffic patterns in and out of Goose Island as they redevelop that part of the city. So, and then you see a line along the lakefront looking at the lake effect for air pollution and weather. And, you know, we try to get to, I don't think we're in every one of the 77 neighborhood areas, but that's been our aspiration is, and the way we've carried that out is every time we think we're going to put one in this neighborhood, we make sure that the aldermen, the community groups there are interested in having something like this, and that there are scientists that are saying we want data from that location or a location like that. And so far, every time we've gotten a request, and there have been a dozen or two from a community group or an individual that says, can you put a node here? We've made good on that. So some of these, about 24 of these, have been put there because somebody, a community group or an individual, has asked for the node to be put in that place. Okay, real quickly then, just so we have time for Q&A, all the data is open and free. You can go to the Array of Things website, Google Array of Things, you'll find it, arrayofthings.org. You can bulk download the data. You can use an API that has data that's less than 5 minutes old. The bulk download could be as long as 24 hours old because we do that push once a day. All of the data here is open and free. None of the images are open and free. Those are all kept secure, and you have to have a data use agreement to access those. I mentioned engaging communities. We've done some really fun stuff with high school students at Lane Tech, including working with the Cubs organization to put some combinations of weather measurements, noise measurements, and a few others in and around Wrigley Field. We've had about 600 students come through the program at Lane Tech. It's been led by Jeff Solon and Dan Law there, who are 2 faculty members. In the upper left, you see I'm actually wearing the shirt I'm wearing today, sort of peeking from behind the students. That's just one of the annual pictures of our student team. We usually have 15 to 20 students a year. In the upper right, you can see some of our public meetings. You can go on the web and look at our privacy policies. In a nutshell, I've already described them. It was important for us to have very strong, transparent processes and accountability. And so you can see our advisory team here is a very diverse collection of people, from university provosts to the president of the School of the Art Institute of Chicago to privacy lawyers and community organizers, and so we've really benefited from advice from such a diverse group. So in closing, we do have this next project that's happening called SAGE, where we officially coined the term software-defined sensor. And this is to go beyond cities to look at two other contexts of software-defined sensors, one of which is a nationwide network of environmental and ecological measurement stations that include, in some cases, people that are taking water samples and counting bugs, to flux towers that are, there are about 80 of these towers across the country that are measuring different atmospheric conditions. And the interest on their part in software-defined sensors is because many of these devices are on the other end of a slow network, they want the devices to be able to automatically detect interesting conditions and adjust their measurements to capture as much data about those interesting events or conditions as possible. Because right now they're just, even though they can sample certain things several times a second, they throw out all but a 30-second sample because they don't have a way to send all that data. So that means that when you want to sample something at 10 times a second, you've got the device that's hardwired to only do every 30 seconds. So intelligence at the device would allow you to do that. Then the other project here is in Southern California, about 100 towers with cameras and smoke detectors and other things. And that's where we're doing work to understand whether we can, and to what degree we can recognize smoke from a wildfire and then use all of the sensing devices in that network of 100 towers to feed real-time data to a computational model that's running on a supercomputer at the UC San Diego, which is a sister center to, or brother center to the National Center for Supercomputing Applications, NCSA in Urbana. So we want to stream that data there while they're running a real-time simulation of that fire, and can then say, based on real-time data in our predictive model, that fire is going to start to, veer in this direction or that direction. So that's a new project. It is targeting not what we can do today, but the rapidly approaching future where there are very powerful IoT, Internet of Things devices, sensors that are connected with high bandwidth networks like 5G. And there are millions of those. And then on the other end of the spectrum are machines that are 1,000 times faster than we have today, like the Aurora Supercomputer that's going to start arriving at Argonne in a year or so, or the end of next year, the nation's first exascale machine, a $500 million supercomputer right outside of Chicago. So how do you program this, what we call the continuum? How do you program this environment so that you can take advantage of everything from the sensors at the edge to the supercomputer and the things like Array of Things that are on poles? And so you have this situation here, as I've just described, sensors with the use of machine learning and the use of supercomputers. And that requires what's called a programming and runtime environment. So here you see the high-level blueprint for the SAGE project. We started last fall. It's a $9 million project for 3 years. And we've defined 4 different user communities that you can see across the top. And what is the software infrastructure and what are the services they need in order to do the things that they do? So I'll just pick one of them, a developer that says, well, I'm a machine learning person. I'm working with social scientists to figure out how people bunch up in ramps at Wrigley Field or something like that. So the social scientist says, well, I could send a grad student out there and try to take notes or take a bunch of pictures, but they would partner with a machine learning expert, a computer vision expert, and develop code, the bunching at Wrigley code. And then they want to be able to test that code, put it into a library that can then run in these devices. And then somebody else, like an experimenter who doesn't want to develop something new, says, oh, there's edge code in that library that counts people bunching up. So I don't want to use that at Wrigley. I want to use it at my rail station. And so I'll just do some experiments using that code. So we had to define this environment and then start to march down the road, all the while targeting the environment that will be available, broadly speaking, in just a few years, and trying to simulate that environment with our devices today. So I'll close there with 7 minutes left for questions. I'm sorry I didn't, I promised to monitor the chat as well, and I didn't do that. So I'll take
I haven't seen anything come through on the chat yet, Charlie.
All right. So anyway, so I'm delighted to have a chance to speak with you. And the TechReady is an exciting program, part of the things that we do at DPI.
Thank you, Charlie. So, as you were talking, one of the things that came to my mind as being part of the TechReady initiative is what types of skills were needed to execute these arrays. And, and yeah, if you could elaborate on that for
Yeah,
our listeners, I think that might be interesting.
that's a perfect question for, for the Tech Ready program. So, I mean, another way to answer that is when we were staffing, when we are still staffing up for this new project, what kind of skills are we looking for? I think there are a couple of them. They're very specific, right? So almost all of the machine learning that we're doing is using Python libraries. So we're looking for people who are very good at Python programming. Almost all that we do, despite the fact that we have supercomputers at U of I, in Urbana, and at Argonne, almost all that we do, there's some aspect of it, sometimes a large aspect, like all of the data publication API, the downloads, that's all cloud computing. So we also look for people who really understand how to create an environment and maintain that environment in a commercial cloud like Amazon Web Services is what we're using today. And so people who are familiar with system administration in the cloud, and for that matter, those devices that are in our nodes are Linux devices. So we need people who are skilled at administering Linux devices. We need people who are skilled at Python, at cloud computing. Cybersecurity is super important. Everyone that works on our team has to be very, very familiar with the principles of cybersecurity. That doesn't mean they have to be an expert. So those are some of the things that we look for in terms of tech skills.
Thank you, Charlie. Does anybody else have questions? Let me see. So you mentioned cybersecurity. How do you protect the array of things from security threats?
So a couple of things. One of my first jobs was putting in a computer at the University of Illinois that was one of 6 on what was then the backbone of the internet. And at that point in time, nobody really architected into the internet the notion of security because it was assumed it was just, computer scientists talking to each other. And that hit really hard in 1989 with this thing called the Morris worm. You can Google the Morris worm sometime. It cost me a couple of all-nighters. So with Array of Things, we wanted to design security in from the bottom up, not add it later. And so we did a couple of things. Number one, the software that runs out in the node will only run software that is digitally signed by one of the people on our staff. So there are a finite number, 2 or 3 people that have the passcode in their brain and can sign code. And so, even if somebody were to physically break into the device and try to reprogram it, they wouldn't be able to do that because it would refuse to run the code. All of the devices also run with we call no open ports. So if I want to connect from my laptop to Zoom, what happens is my laptop sends a message to Zoom with a specification that says I want virtual port 23 or whatever it is, probably not 23. And so Zoom has to be listening for me to ask to make a connection. That means that there's a window of opportunity for me to send something to Zoom that breaks Zoom, that gets in, that causes me to get in and have more privileges than I should have. So we run no open ports. That means that when these devices go up on the poles, there's no way for us to contact them. It's not possible because they're not listening to the radios. They have to contact us. So it's a one-way communication. And then when they go up and they get power, they make a connection back to us, and that's how we can talk to them. And then all the communications are encrypted. So the number of things that we did like that were really trying to build in cybersecurity right in the skeleton of the system.
So Charlie, how do you upload new software programs to have it run new analyses?
Well, that's where it's important for the device to connect back to us. So right now what's happening is when the device powers up, it makes a connection back to a secure server at Argonne. And through that connection, it's sort of like we can talk to it on the phone, but it has to call us.
Okay.
People's cell phone, it's like they never answer it, but you get a call from them. It's the same deal here. So we can
Okay.
still upload software, but it has to make the connection back to us.
Interesting. Anybody else want to just open up your chat line or your microphone and chime in with a question? Now is the time. We're running short on time here. Well, I don't know if Charlie, do you have a 1 o'clock?
Nope.
So if anybody wants to hang on, I think we'll close up officially. But if anyone has a quick question they'd like to ask after we turn off the recording, you can linger for a few minutes. But if you have things to get going to, feel free to do that as well.
We have a question in the chat, Karen.
Oh, thank you.
So Joe is saying, my son was involved with the Array of Things project while serving as an intern at Argonne some years ago, but is hiring for AOT related positions still done through Argonne or directly through DPI?
Good question. And I'm sure I met your son if he was in the project. For the Array of Things, that project has essentially concluded and become part of a new project called SAGE. The new project called SAGE, so at the time we were hiring people, I was at UChicago and Argonne, so we were hiring people through UChicago, Northwestern, and Argonne, and also NIU for that matter when it came to students. Today, it's largely the same, except DPI is another option for hiring. I don't know why my video turned off.
I did it, sorry.
Oh, did you want me to turn it off?
I was just trying to unshare your slide so I could get my last slide on.
Well,
Sorry.
well, I thought maybe I was like making bad. So now the SAGE project is a grant from NSF to Northwestern University, and it has sub-awards that go to other universities, including DPI, UChicago, Argonne, and NIU. And then there's some others outside the state of Illinois. So all of those groups have the ability to hire full-time people in some cases, and in other cases, students. For the most part, I would say if your son is interested in a full-time post, education job, we're doing for the SAGE project, most of the new hires are coming through Northwestern. That's just because it's easier to manage within one institution. So.
Okay, and let me make my final plug here. Thank you for coming, everyone. Thank you so much, Charlie. This was a fascinating presentation. I got a lot out of it personally. As a reminder, we'll be sending out the recording of today's webinar. I expect to see that in the next couple days. We'll also include an invitation to next week's webinar, which is Security Threats and Mitigation with Venkatakrishnan. He's another research and development person from DPI, and I'm sure that will also be fascinating. Another couple of reminders, we're going to be posting the video on our YouTube channel. We also have LinkedIn and Facebook accounts, so if you like what we're doing, please follow us and like us on those two channels. Thanks again and have a great day.